In this lecture, we'll take a look at some different programming paradigms and see how they differ from each other.
Computer scientists are fond of the word paradigm. Now, a paradigm is a model or mental framework for representing or thinking about something. The paradigm for procedural programming languages says that a sequence of detailed instructions is provided to the computer. Each instruction accesses or modifies the contents of a memory location, and if the computer carries out these instructions one at a time or sequentially, then the final result of all the memory cell manipulations is the solution to the problem at hand. Now you might think, this sounds a lot like our definition of an algorithm. Well, it does sound a lot like a definition of an algorithm. In fact, programming in a procedural language consists of planning the algorithm and then capturing the unambiguous and effectively computable operations as program instructions. So what this means is, in a procedural programming language, we must pay attention to the details of exactly how the computer is going to accomplish the desired task in a step-by-step fashion. Now, in object-oriented programming, the procedural paradigm still holds, but the step-by-step instructions may be split into these small sets that are encapsulated within classes. So what we're going to be doing here is we're going to be looking at programming languages that use alternatives to the procedural approach. So we're going to be looking at languages that are based on other paradigms. In fact, we're going to look at three different types. We're going to look at functional programming, which is basically a combination of various transformations on items. We're going to be looking at logic programming, and this is going to consist of a series of logical deductions from known facts. And then we're going to look at parallel programming, which means that we can have multiple copies of the same subtask, or we can have multiple subtasks of the same problem. But the key thing here is that these tasks would be performed simultaneously by different processors. We'll start by taking a look at functional programming. Functional programming had its start with the design of the Lisp programming language by John McCarthy at MIT in 1958. Now, Lisp stands for list processing. So this is a language that's focused on dealing with functions, transformations, and lists specifically. And this is actually the second oldest programming language, with Fortran being the first. And there are several variants of the language. One of the languages that we're going to be looking at later is called Scheme, is a variant of Lisp, and was developed in the late 1970s. A functional programming language views every task in terms of functions. Surprise, surprise, right? That's why it's called a functional language. But unlike the more general usage of the word function in some procedural programming languages, the term function in this case is more along the lines of mathematical functions. So we're taking in some kind of argument and we're doing something with it to compute a single value. So more formally, when the arguments are given values, the function will transform those values according to some specified rule into a corresponding resulting value. So what we're saying here is that we can think of a program as a function that acts on some input data. So the arguments would be our input, and then we would transform that input into our desired output or compute some single value. Now, in a functional programming language, there are certain functions that are called primitive functions or just primitives, and these are defined as part of the language itself. There are other languages that can be defined by the programmer. So we can use either already existing primitive functions as part of the language, or we can define our own functions in the language. Let's take a look at an example of a function in Scheme. That way you have an idea of how a functional programming language works. So let's say we're going to define the square function in Scheme. So this would be the actual definition. I know this looks very different from what you've seen before. Now, let me explain what's going on here. So the define keyword means that we're creating our own function. And the name of this is going to be called square, and it's going to take a single argument called x. So that's this part right here. The part down here is going to be the actual definition of the function. And in Scheme and languages similar to that, The way we notate mathematical computations is a little different. Instead of having the operand and then an operator and an operand, we put the operator first and then two operands. So this is the same thing as saying x times x is all we're saying here. So like for example, if we have the user enter square 3, it's going to compute 3 times 3 and output 9. And what's really nice about this is we can take a defined function and use it as a definition in other functions. So let's just do another example. Let's say we want to define a function that computes 2x squared. So we can create a definition of that. So we're going to define a function which we'll call polynomial, and it's going to take a single parameter x. And take a look at the definition. So the definition is actually down here. And yes, there are a lot of parentheses involved with this. In fact, with Scheme and Lisp, one of the more annoying parts of it is just making sure you handle the parentheses correctly. But here, we're going to multiply 2 by the result of square x. So we can actually call the square function inside of it and then take that result and multiply it by 2. So like in this case, if we do polynomial 3, well, what's going to happen here is it's going to be the same thing as taking 2 times the square of 3. Well, 3 squared is 9, and then you multiply that by 2, and you get 18. So the whole point here is that we can build these complex combinations of functions and use the results and apply that to other functions. And then those can use the results and apply it to other functions and so forth. So functional languages are sometimes called applicative languages just because they have this property where we can repeatedly apply functions on top of other functions. As the name Lisp implies, Lisp will process lists of things, and so does Scheme. In fact, the arguments to functions are often lists. As a trivial case, nothing can be thought of as an empty list, which we would call nil, N-I-L. So we're going to be looking at 4 primitive list processing functions that are available in Scheme. The first one is called list, and this is a function that can have any number of arguments, and its action is just simply to create a list out of those arguments. So for example, if we have something like, in parentheses, list 345, this will evaluate the list 345. So the output would just be 345 in parentheses. The next function we'll take a look at is called car. Yes, that's right, it's car, as in the automobile. This takes in a non-empty list as a single argument, and it basically produces, as a result, the first element in that list. So for example, if we have something like car and then list 345, it's going to output 3 because it's the first item in the list. The next function is what's called cdr. You know, it's spelled CDR, but it is pronounced cdr. And what this does, it also takes a non-empty list as its one and only argument, and it produces a list that remains after the first element has been removed. So basically, we've taken a list and we output all the elements of the list except the first item. So it pretty much does the exact opposite of what car does. So for example, if we did cdr for list 345, it would output the list 45. There's one more we'll take a look at, which is called null with a question mark. Yes, that is intentional. And this has a single list as its argument, and it evaluates to true if the list is nil or empty, and evaluates to false if the list is non-empty. So for example, if we did something like null and then pass list 345 as the argument, it's going to output false. Let's use those functions we just defined to create our own function, which we're going to call the adder function. So what this is going to do is we're going to take a list and we're just basically going to compute the sum of all of the items in this list. So let's just kind of walk through what this is doing. So remember, define means we're defining a function, adder is the name of the function, and input list is going to be our argument, which is going to be some non-empty list. Now this con function right here stands for condition. So this is basically an if-else statement. So our condition is checking to see if the input list is null. So, because remember, this null means that we're checking if the argument is empty. So if the input list is null, then it's going to return a 0. And if it's not true, so then we have this else part. The rest of this function is saying we're going to add the car of the input list. So remember, that's the first item in the list with adder of the cdr. So we're going to actually call the function again, but we're only going to deal with the cdr of the list, or the remainder of the list. So we're going to basically keep calling this function and getting the list smaller and smaller until we get to the empty list, and then we're going to work our way backwards and compute the sum as we go. So let's just kind of walk through an example of this just so you can see what's going on here. So let's say we call adder 3, 4, 5. So we're basically going to add 3, 4, and 5 together. Well, if we look through here, the list is not empty. So what that means is this is going to end up being plus 3 adder 4, 5, because we're doing the else part. So we're going to do plus the car of the input list is 3, the cdr of the input list is 4, 5. So now we're going to call adder on 4, 5. Once again, the list is not empty. So this is basically saying plus 3, but then inside of that is going to be plus 4 adder 5. Because in the list 4, 5, the car is going to be 4 and the cdr is going to be 5. So now we're going to call adder again, but our list is going to be just 5. So if we do that, well, we're going to get plus 3, plus 4, plus 5. And the cdr of the list is going to be nil because, I mean, our list is just a single thing. So the car is going to be 5 and the cdr is going to be everything else. Well, everything else is nothing, so it's going to be nil. So when we call adder with nil, the condition at that case is going to be true. So at that point, this adder right here is going to return 0. So what we're going to get now is plus 3, then in parentheses plus 4, then in parentheses plus 5, 0. So now we're going to kind of work our way back. So we're going to handle this part of the operation first. So we're going to add 5 and 0 together, and that's going to give us 5. So now we have plus 3 and then plus 4, 5. We're now going to evaluate the plus 4, 5 part. So that's going to give us 9. So we get plus 3 and 9. We evaluate that, and it gives us 12. So if you notice that in the definition of our adder function, it actually involves calling the adder function again and again, and we just called it on a smaller list. So in our example, we invoke the adder function repeatedly on the list 3, 4, 5, and then the list 4, 5, and then on 5, and then finally on nil. So something that's defined in smaller versions of itself is said to be recursive. So this is actually what we call a recursive function. Now, recursion is one of those features in functional languages that makes it possible to have short and elegant solutions to many of the problems that we need to solve. Now, it is a dominant mode of operation in functional languages, but it is worth mentioning that many of the procedural languages also support recursion. One of the benefits with functional languages is that there aren't any side effects when doing all the computations. A side effect is basically whenever a function would change a value that should not be changed. And the reason why this doesn't happen in functional languages is because instead of working with the memory addresses, we're working with the actual values. In procedural languages, what could happen is we store something in memory, and then some other function, some other operation could change those values in those memory addresses. So we could accidentally or unintentionally change those values. But with functional languages, we're not messing with any memory addresses. So if we're given a value, we're modifying that value and we're not modifying any addresses.